except that here we only want to discuss anomalies. And to discuss anomalies, we actually, life is much easier, because we are not going to look at the full quantum gauge theory. We are only concerned with W of A tilde, which is deep psi bar e to the I s matter, okay, of psi bar and A. And we don't have to deal with the fact that we need to gauge fix and introduce the ghost and all the things. So the question we ask is just whether this thing is gauge invariant or not. And we don't have to go through all these complicated things with a nonlinear BRST symmetry. Okay? So actually what we do is much simpler here. Now let's ask then whether this thing is gauge invariant or not. Okay? Well, e to the I W tilde of the gauge transformed A is deep psi bar e to the I, well, that's Lagrangian, sorry, that's our matter, of psi bar and A prime. Okay, so then again we do similar things. We change again psi's into psi primes, just change the names, then decide that the psi primes are the gauge transformed psi's. Okay, so then this is gauge invariant, so this is L matter of psi prime and A, and the question then is what happens with the measure for the matter fields. Okay, so again this by definition is deep psi bar plus integral epsilon alpha A alpha of x. Either it's invariant and there's nothing, or if it transforms to some Jacobian, it's some expression like this. It must be some local e to the I integral epsilon times A alpha of x term. Okay? Yes? No, you always have a BRST symmetry. You can do it for any gauge group. You construct the BRST symmetry. Yeah, I have some generators T alpha, and I construct it independently of what these T alphas are. Except that at this level, I don't have to consider BRST. Okay, BRST is only in the next step when I do want to integrate over the gauge fields. Then I need to gauge fix and get all the complications. Okay. Okay, now, provided this A alpha does not depend on the matter fields, and it does not, this goes out from the functional integral over the psi's, epsilon alpha A alpha, and the remaining thing is e to the I W tilde of A. Okay, so we get a very simple relation in this case. We just find that the gauge transform W tilde equals the original W tilde plus integral epsilon alpha A alpha of x. Or I put this on the other side. This minus this equals this, and this is just, of course, the gauge transformation, the variation of this W tilde effective action. Okay, so let's write it as delta epsilon of W tilde of A is integral epsilon alpha A alpha of x. So again, my anomaly, which comes from the anomalous transformation of the measure for the matter fields, is related to this variation of this type of effective action W tilde. Okay, let me relate this now to a current non-conservation again. Okay? Well, consider any functional W like this of the gauge field, and I do a gauge transformation. Okay? So by definition, this is W of A plus delta A minus W of A. If this is infinitesimal, I can write this as integral d for x delta A mu of x times the function derivative of this W of A by delta A mu of x. Okay? It's just trivial. And then, what is my delta A mu? It's the gauge transformed. So the gauge variation of A is d mu epsilon of x component alpha. Okay? Now, that's a covariant derivative. A covariant derivative you may always integrate by parts, just like an ordinary derivative. It's one of the things that may be surprising at the first point, but it works. Okay? The covariant derivative is made such that, well, this thing is because the alpha indices are contracted, it's like a scalar, it's a gauge invariant quantity. If you integrate this by part with the appropriate partial derivative, it's again an invariant quantity, so it must work. Okay, so I get a minus sign, and I get that this delta epsilon of this W of A is minus d for x epsilon alpha of x times the covariant derivative of delta this W of A by delta A mu component alpha. Okay, so that's in general true. Now, of course, I take for this W my W tilde here, and I find that minus the integral d for x epsilon alpha of x d mu delta W tilde by delta A mu of x component alpha equals the integral d for x epsilon alpha of x, the anomaly of x. Okay? That's true for any epsilon, so the anomaly equals this thing. So d mu delta W tilde by delta A mu of x component alpha equals minus the anomaly of x. Now, what is this? The delta W by delta A mu. Okay, that was the definition. Okay, this is my W here. If I take a derivative with respect to A mu, let's do this. Delta by delta A mu alpha of x of I W tilde of A. Okay, IW is the logarithm of this. So the logarithm of this I get in the denominator deep psi bar e to the I L meta, and in the numerator I get a deep psi bar delta by delta A mu alpha of, well, the integral L meta e to the I L meta. Okay? But the derivative of the meta action with respect to A mu alpha by definition is the gauge current, the meta gauge current. Okay? This is J mu alpha meta of x with an I. There was an I here, an I there. So what this thing by definition is the expectation value of J mu. Okay? So this is d mu, the expectation value of J mu alpha. Well, J mu of x, the whole thing alpha. So we find again that the covariant derivative of the expectation value of the meta current vanishes if there's no anomaly, equals minus the anomaly if there is an anomaly. Now, I've not computed this anomaly yet, okay? I just say if there is one, and I defined it as the fact I get from the transformation of the measure. But it gives us a dictionary which we'll use later on. So delta L meta by delta A mu, what is it? Well, J mu alpha is I psi bar gamma mu T alpha psi, right? That's my current. So that's a very similar formula to what we had for the abelian anomaly, where we had the current with the gamma 5 here and the corresponding abelian anomaly. Now it's the anomaly under gauge transformations. Okay. 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 So what I want now is, well, as I said, I haven't determined this thing yet, and we will not determine this anomaly for the gauge transformation from computing a Jacobian. We do it in a different way. Okay. We will obtain this thing here from a Feynman diagram computation by computing the triangle diagram. So what we need is to relate this relation, to take this relation and to see how it can be related to the computation of a Feynman diagram. So this goes under the anomalous word identities. Okay. I've just argued that delta by delta A mu alpha of x of this W tilde of A was the expectation value of J mu alpha of x, okay, computed, of course, in the presence of my gauge field A, okay. This was just, that's just deep psi bar, J mu alpha of x e to the I s meta divided by deep psi bar e to the I s meta, okay. Okay. Now, if I take further derivatives with respect to A mu beta of y, well, that depends on A, it's this thing. So taking further derivatives, S meta depends on I get a J mu here, but I can also derive this. So this combines with a minus sign to compute the connected correlation function, okay? So taking one more derivative will give me the expectation value now with a J nu, well, not nu, J nu beta of y. And because we get these two currents inserted in the functional integral, we know that it computes the time ordered product of these currents, okay? And I can take one more derivative or any number of derivatives. So if I take delta by delta A mu 1 alpha 1 of x1 there's an I here also, delta by delta A mu n alpha n of xn of W tilde of A, this thing computes as an I to the n minus 1, the time ordered product of J mu 1 alpha 1 of x1, J mu n alpha n of xn, connected, and it's still in the presence of A, but after having taken all these derivatives, I set A to 0, so that's then for A equals 0, okay? So from this W tilde, I can generate connected correlation functions for an arbitrary number of currents. So what I want to use then is like this relation here, and taking further derivatives with respect to A. Okay, so I will get further currents inserted here, and on the right hand side my anomaly, which depends on the gauge field, by taking functional derivatives I will suppress the gauge fields. Okay, so and then we get corresponding identities between these current correlation functions, but these time-ordered, these things there, they have a nice interpretation in terms of Feynman diagrams. Okay, these time-ordered products of currents, well, for example, the time-ordered J mu alpha of x, J nu beta of y. This is just, well, you have x, you have y. You sort of could attach gauge fields with the mu alpha here. You could attach gauge fields with the nu and beta. And you are the j's, each j of course is a psi bar, gamma, mu, t, alpha, psi. This is a psi bar, gamma, nu, t, beta, psi. So when you compute these correlation functions, you're instructed to contract these guys, you get propagators, and of course you compute this Feynman diagram, right? So this thing in general computes the endpoint function, one loop, because with only the integrating only the matter fields, you can never get anything like an internal gauge boson propagator. So necessarily these are one loop, okay? And these are the same as the proper vertices, which you get from the gamma, mu1 to mu n, alpha 1 to alpha n, x1 to xn, by restricting this to one loop. They're the same as the endpoint vertex functions at one loop. So for example, if you put 3 currents j, well, then you compute a triangle, okay? Okay. Now, on the other hand, so we want to start with this relation there, and relate it to something we can interpret in terms of Feynman diagrams. Okay. So let's do this first for the abelian anomaly, because we know the result. Okay, for the abelian anomaly, we know that d mu, expectation value of j mu 5 in the presence of a gauge field, equals minus the anomaly, okay, minus the abelian anomaly of x, which is 1 over 16 pi squared, epsilon mu nu rho sigma, trace t alpha, f mu nu, f rho sigma. Okay? Now what we want to do is take two functional derivatives with respect to a. And that's at x here. That's at x and that's at x. So we're going to take a delta by delta a nu beta of y and a delta by delta a rho gamma at z. Now this d mu here is a d by dx mu. Okay? So x is different from y and z. So these functional derivatives, they go through this spatial derivative. They act on the a, which is hidden in here. And this, so on the left-hand side, we're going to get a d by dx mu of j mu 5 of x, j nu beta of y, j rho gamma of z, a. And on the right-hand side, we take derivatives of these f's of a's with respect to z. So we're going to get a delta of y minus x, a delta of z minus x, and a certain bunch of factors. So which is, so when we take derivatives, we get a 2, we get another 2, we get an 8, we're going to get a 1 over 2 pi squared. Okay. Okay, yeah. We're going to get a trace T alpha, T beta, T gamma. And we're going to get the epsilon mu nu rho sigma. We get a d by dy, y is nu, a delta 4 of x minus y. And we get another d by dz rho, delta 4 of x minus z. Something like this, okay? We could take a further derivative with respect to a, and then we would get 0 on the right-hand side, because there are only 2 a's in here. No, that's for the abelian, sorry, okay. That was too simple. Plus, no, okay. Now we could get further, but then we take a to 0. Check. And I was doing this only for, these guys are also u1s, okay, to simplify. Take a to 0. So what we get then is a relation between, this is a 3-point function, okay, forget these gammas. That's a 3-point function. We can interpret this in terms of a Feynman diagram. Mu nu rho, where we probe for conservation of the current at the point where we put a j mu 5 here. So at this vertex we put a gamma mu gamma 5, okay? So we can compute this triangle diagram, and we Fourier transform, of course, because we always do Feynman diagrams in momentum space. Now to Fourier transform this, we multiply this with the exponentials e to the ikx, e to the ipy, e to the iqz. And, well, if you Fourier transform this, you get on the left-hand side a relation for this 3-point function, gamma 5 mu nu rho, which depends on p, q, and by momentum conservation on minus p minus q. We multiply with p plus q mu for this vertex. And on the right-hand side, these derivatives you integrate by part, they will give me factors of p and q. So on the right-hand side, if I do this correctly, let me just skip a few lines. So correctly I have a minus I here, and here I have a minus 1 over 2 pi squared. So this was abelian now, so I get a sum of the u1 charges cube. That's from my trace. Epsilon nu rho lambda sigma p lambda q sigma. Okay, so that's the translation of my relation up there. D mu expectation mu j mu a is the anomaly. I took 2 functional derivatives. The left-hand side relates to a 3-point function, so that's just this with a gamma nu, gamma rho, gamma mu, gamma 5 vertex. And we multiply with the momentum on this vertex to check whether this current is conserved. And on the right-hand side from the anomaly, we get this expression. Okay. So this we got from our computation of the Jacobian, from the transformation of the measure. But we can now, of course, compute this Feynman diagram. We know the Feynman rules, we compute it, and we check that if we compute this, we indeed get exactly this factor. Okay. Now I'm late, of course, I will not do this today, I guess, we'll do this tomorrow. What I want to do now is do exactly the same thing, not for the abelian anomaly, but for the gauge anomaly, where we haven't computed the right-hand side. Okay. We don't, for the anomaly under gauge transformations, we don't know what the right-hand side is, but I want to set up the same dictionary to relate this to a Feynman diagram computation. Okay. So So for the non-abelian gauge symmetry, we start with a similar thing. We start with the covariant derivative of the gauge current expectation value, which is minus the A alpha of x anomaly, okay? And I take successive functional derivatives with respect to the gauge field. Now the difference now is that this d mu is actually a d mu j mu of x alpha plus a term which is c alpha beta gamma a beta mu of x times j mu gamma of x. Okay. On the left hand side I have an explicit appearance of A. So when I take functional derivatives, the functional derivatives will either act on this one and introduce further currents in the expectation value, or they can act on the A mu here. So I get more terms. Okay. Okay, so this equals minus A alpha of x. So if I take one functional derivative here, delta by delta A nu beta of y. Okay, get a first term here, which will be d mu, expectation value of j nu beta of y, j mu alpha of x, a, and there's an I, okay. And the second term, I get two contributions. I get from this one, I'm going to get a, beta, not beta, this should be delta, okay. Okay, so I get a delta beta delta nu mu, so I'm gonna get a c alpha beta gamma, nu is mu, that's nu. I get a delta 4 of y minus x. I get a j nu gamma of x expectation value. And on the right hand side I get a minus delta a alpha of x by delta a nu beta of y. Okay. And I get, sorry, I forgot to take this one also. I get a plus c alpha delta gamma a mu delta, and then expectation value of j nu beta of y, j mu gamma of x. Sorry, it's getting messy here. I get three terms on my left hand side. Okay. Then I take one more derivative. Okay, one more derivative, and I get, well, so one more derivative. I get from the first term something, I get an I square, I get a minus d mu, which is a d by dx mu, j rho gamma of z, all this is time ordered of course, j nu beta of y, j mu alpha of x. Okay. I get here a term which is a plus c alpha beta gamma a delta 4, j rho gamma of z, j nu, no too many gammas. Let this gamma be epsilon. So this is epsilon, j epsilon of x. Okay. And from here I get again two terms. I can derive this a, so I get a plus c alpha delta gamma, and I get a delta 4 here, and another one with t jj. Let me not write it out. And then I get a term with an a and jjj. But I'm going to set a to 0 in the end. So once I set a to 0, I don't get the extra term. And on the right hand side, I get a minus delta 2 a alpha of x by delta a rho gamma of z delta a nu beta of y. Okay, so this is a 3-point function. These are 2-point functions. Okay, so this is a d by dx mu of a gamma 3-point function, mu nu rho alpha, beta, gamma of x, y, and z. And then I get two terms, C alpha, beta, epsilon, a two-point function, gamma, rho nu, alpha, beta, epsilon, gamma. I get another C alpha, delta, gamma, another two-point function. And on the right-hand side, I have my derivative of two derivatives of my anomaly function. Okay? So this is my ward identity. Without this, it's the normal ward identity. With this term, we call this an anomalous ward identity. And we can check this by doing a Feynman diagram computation. Okay? So of course, we don't know yet what this thing is, but if we assume, for example, that this has a certain form, okay. So everything on the left-hand side is computed for a equals 0. So if I make an assumption about the quadratic term, so my quadratic term in my anomaly, I will assume that it has the form some constant. Again, some epsilon mu nu rho sigma. Trace T alpha. No. 4c. Let me put a 4 here. D mu a nu d rho a sigma. Okay. If I assume it has this form, and we will see that it does have this form, then taking two derivatives, and again taking the Fourier transforms, will give me something of the form epsilon mu rho sigma, p rho q sigma, which I can relate to exactly these terms here. So what we will do is we will compute the three-point function, check for conservation. So we do, of course, the Fourier transform. We compute the gamma mu nu rho alpha, beta, gamma of minus p minus q, p and q. We multiply with p plus q mu. Okay. So if you compute this, there should be a term which relates to the two-point function. So these guys are just vacuum polarization tensors. Okay. So this is my three-point function, where I probe for conservation in one of the vertices. So this should be vacuum polarization plus vacuum polarization, which would correspond to these terms, plus anomaly, plus whatever we get from here, okay? Plus d delta a alpha by delta a delta a. Okay. Now, we will do this computation. We will find there are two terms in here. There's one term with an epsilon tensor, which will correspond to the anomaly here, exactly of this form. And there are terms without the epsilon tensor, but with structure constants, which exactly correspond to these vacuum polarization tensors. And from this computation, we can then read off this coefficient C here. Okay. So that's the next step we want to do. Okay, there's still some time. Question maybe? Yeah. No. No. What I know is that I have an infinite set of ward identities. So I took two derivatives with respect to A, I set A to 0. But I could have taken three derivatives and then set A to 0, four derivatives. So you can derive an infinite set of ward identities, which relates. So the simplest thing is three-point function, which is related to two-point functions, and the derivative of the anomaly with respect to two gauge fields. I could have taken one more derivative, and I would have found a relation between a box diagram, where I probe for conservation in one of the corners here, and on the right-hand side I would have found triangle diagrams and a third derivative of A with the anomaly with respect to gauge fields. And then I could have taken further derivatives, and I would have found a relation between the pentagon diagram and boxes and maybe even triangles, I don't know, plus a fourth derivative of this with respect to A. These are just water identities I derive from some so far unspecified form of my anomaly. Okay? Okay. So then I compute my triangle. I get the non-anomalous terms plus something, which I say which must be this. So what I infer from this is delta 2 of the anomaly by L at A equals 0. So what I get from this is the term in the anomaly that is quadratic in A. Then I should compute the box diagram and get the term that is cubic in A. And then I compute the pentagon and get the terms that are quartic in A, and so on. Now, I could have started even less, just not the triangle, but just this thing, and the water identity for this. So then I would have had on the right-hand side delta A, the variation of the anomaly with respect to one gauge field at A equals 0. But we suspect that, because it's quadratic, that wouldn't give anything. And indeed, it doesn't give anything. Okay? So I compute all these Feynman diagrams, I check for conservation, and I reconstruct my anomaly functional. They are order A cube terms, of course, here. Okay? So these guys you get from the box diagram, and terms of order A to the fourth from the pentagon, and so on. So that could be the program. Now, I don't want to do infinitely many Feynman diagram computations, so I will sketch this computation, which will give me the term in A that is quadratic in the gauge fields. And then I will say, aha, later on, we'll find some clever way to relate the cubic terms to the quadratic terms, and the quartic terms to the quadratic terms. They're all related, so it's enough just to get this single coefficient. That's the strategy, okay? Yes? No, this was sort of just a, well, no, this was sort of a remark with the abelian anomaly. Okay, now it's, well, you have this TA, and this is d mu a nu d rho a sigma. You may think that maybe this comes from f mu nu f rho sigma, but it doesn't. Okay? So for this gauge anomaly, it's certainly not related to instantons. Not this direct way. Okay? This was true for the anomaly under this abelian transformation with the gamma 5. Now we look at anomalies under gauge transformations. And you may think this comes from, no, these non-abelian f's are called d mu a nu, but then there's the commutator a mu with a nu term. Okay? So if we had these f's, well, the cubic term is not the one which comes from ff. So this is not a quarter trace T alpha f mu nu f rho sigma for the gauge anomaly. It's not. In particular, this would give a term quartic in the A's, and there's no term. We will find there's no term a to the fourth. Okay? There's only a cubic term there. So In the notes, I wanted to do this Feynman diagram computation first for the case of the abelian anomaly, but let's just go directly to the case of interest, which is the gauge anomaly. And let's not really do the computation today, but let's just set out the stage for this computation. If I look at matter fields, psi, that are ordinary Dirac fermions, so with a meta Lagrangian minus psi bar d slash minus I a slash psi, okay, maybe with a mass term, there is going to be no anomaly. Okay, there's no anomaly because I can, I can compute all my Feynman diagrams. In particular, I can compute this triangle diagram. So you attach the gauge bosons here. You compute the triangle with the Dirac fermion running around, and of course this is divergent. Okay. Every propagator will give me 1 over I p slash. So this diagram is some d4k or k slash. Okay, so I'm going to have a trace. I get gammas 1 over k slash, gamma 1 over I k slash plus p slash, gamma 1 over I k slash. So this goes like 1 over k to the cube. And this diagram is linearly divergent. So I have to regulate it, as always, well, not always, like any divergent diagram. And if I've just Dirac fermions, the most convenient way to regulate this is to do dimensional regularization. Okay? Dimensional regularization preserves the gauge invariance. So my regulated diagram will be gauge invariant, and once I finish computing my triangle diagram, there are going to be some divergent pieces. I know I can add gauge invariant counter terms, and as a result I'll get my ward identity between this triangle contracted with P plus Q, this vacuum polarization tensors, and no anomaly, because the anomaly translates a current non-conservation, so it translates a gauge non-invariance of my fermion measure, right? Deep psi bar, and because I know I can regulate everything in a gauge invariant way, there will be no manifestation of gauge non-invariance, and there's no anomaly. So you may ask, what are we talking about? Well, we're talking about a Lagrangian which is not this one. Okay? If there are anomalies, we are talking about a different meta-Lagrangian. We are talking about not Dirac fermions, but we are talking about chiral fermions. Now, a chiral fermion is a fermion which is only, say, left-handed or right-handed, which only has positive chirality or negative chirality. So we introduce chirality projectors, 1 plus gamma 5 over 2, and PR 1 minus gamma 5 over 2. So you could call this P plus and this P minus if you wish. They project on positive and negative chirality. So any Dirac fermion, psi if you wish, is a sum of psi L plus a psi right, with the psi L being the left projected thing and the psi R being the right projected thing. Okay? So we want to look at a theory where the matter fields have only one chiral part, maybe only the left-handed ones. Okay. So my meta-Lagrangian is minus psi L bar d slash minus I a slash psi L. No right-handed part, okay? So then there's a gamma 5, of course, in the game, and again, it's because of this gamma 5 that we're gonna get something after computing some trace, some epsilon tensor, and we're going to get the anomaly. Now, this Dirac meta thing, I could have written it as minus, okay, there's one thing before I should tell you. If you take psi L and you take a bar of it, it means taking psi L dagger I gamma 0, okay? Now these projectors are Hermitian because gamma 5 is Hermitian, so I can write this as psi PL psi dagger I gamma 0. So this is psi dagger PL dagger, which is PL I gamma 0. And because gamma 0 anticommutes with the gamma 5, this is psi dagger I gamma 0 P right, which is psi bar P right. Okay? So the bar of a left-handed psi is sort of a right-handed thing. So then if I write psi L bar d slash psi L, so this is like psi bar PR d slash PL psi, but then this PL, if you take it through the gamma in the d slash, it becomes a P right, and P right square is P right, so this is non-vanishing. However, if you look at psi L bar psi L to write a mass term, well, then this is M psi bar PR PL psi, so this is 0. So you cannot write a mass term for a chiral fermion. Chiral fermions necessarily are massless, okay? And, well, what I want to say, my Dirac meta term, of course, I can write it as the sum of psi L bar d slash minus I a slash psi L minus psi R bar d slash minus I a slash psi R. I may view this as a sum of two terms for a left-handed and a right-handed fermion. But now we want to look at a chiral meta-Lagrangian, which only has a left-handed fermion. Okay? So we need to we want to compute the Feynman diagram, so we need the Feynman rules for this thing. And as I said, we cannot write a mass term here, okay? So that's necessarily, these are massless fermions. Well, I can write this, of course, as what? I can write this as minus psi bar d slash minus I a slash PL psi, right? As I said, it's enough to have one PL. I can take it through, it's a PR, and then it gives me also the psi left here. Okay? So if I want to look at the Feynman rules, what I find is that my propagators, which come from the free part, the propagators are 1 over I P slush, and I should project on a PL here on the left. These are my propagators. I have only the left-handed part propagating. And my vertices come with the A slush. So they come with a gamma mu, T alpha, and a PL. Now in any one-loop diagram, I always has propagator, vertex, propagator, vertex, propagator, vertex, okay? Or vertex, propagator, vertex, propagator. So I will have a vertex, gamma mu T alpha, PL for my vertex. Then comes my propagator, PL 1 over IP slush. Then comes the next vertex, next propagator. But PL is just PL. So I may just erase this PL here. it gives the same thing. Okay? So it's just like saying, okay, my propagator is just a 1 over IP slush, but my vertices have a PL. So these Feynman rules gives me exactly the same result for any one-loop Feynman diagram I'm interested in. Now, but that's like having a propagating Dirac fermion with only the left-handed part coupling to the gauge field. I would get exactly the same Feynman rules from a L tilde meta-Lagrangian, which is minus psi bar d slash psi minus minus I minus psi bar minus I a slash PL psi. Okay? Propagation vertex. So this is the same as saying it's minus psi r bar d slash psi r minus psi l bar covariant derivative psi l. So it's like saying that the left-handed fermion couples with the covariant derivative, which is gauge invariant, but the right-handed fermion does not have covariant derivative, which is not gauge invariant. Okay? So turning things this way, you already suspect that if we compute with such chiral fermions, we may rewrite things as having a full Dirac fermion, but with only the left-handed part coupling to the gauge field. So that's already bound to give us something which possibly is not gauge invariant. Now, if you look at a tree diagram, I don't know, anything like this, well, it's not a problem that the right-handed part doesn't couple to the gauge field, because if you only have external left-handed fermions, you'll never see the right-handed part. But if you have a loop, you'll have the left-handed part propagating and the right-handed part propagating. So in the loops, you'll see this non-gauge invariance due to this right-handed parts. Okay? And now once we have written the meta-Lagrangian like this, with the left-handed and the right-handed part, we could even think of adding a mass term, because now we have left-handed and right-handed. Okay? Of course, it's not there, but when we compute our Feynman diagram, we'll need to impose some regularization because it's divergent. Okay? This is, again, it's linearly divergent, and we have to do something. Now, again, dimensional regularization now is not a good idea, because dimensional regularization means that mu, instead of going from 1 to d, well, 1 to 4, it's going to run from 1 to d, which you can consistently implement unless you need to define the gamma 5 as the product of gamma, well, 0, gamma 1, gamma 2, gamma 3. So this was from 0 to d minus 1, actually. Okay, 0 to 3. So now you need that there are exactly 4 gamma matrices to show that this gamma 5 anti-commutes with any of the gamma mu. If you have not just 4 gamma matrices in here, but then, well, you can't consistently implement a gamma 5 that anti-commutes with d gamma matrices if d is not an even number. Okay? So dimensional regularization is not a good idea. So what we do then is a much older way to regulate, which is Pauli-Villars. Okay? Pauli-Villars is, we have an any loop integral. Let me just write down one thing. So for example, in a, I don't know, vacuum polarization or so, we would have a integral d4k 1 over k slush. In a massive theory, we would have I k slush plus m, and you would have 1 over I p slush minus k slush plus m. Okay? So now we are massless. This is quadratically divergent. So what Pauli Villars does is we add another matter field, which is massive now, but which has opposite statistics. So it gets subtracted 1 over I k slash plus m, 1 over I p slash minus k slash plus m. Okay. So then the large k behavior of the integrand is improved, because for large k, you can neglect the m, they have the same behavior, and the leading divergent cancels. If that's not enough, you can add several Pauli Villars fields. So plus, that's an m1, you add another one with an m2, and a third one with an m3. So you add enough to cancel all the leading divergence, all the divergences. Okay. Now, again, for a chiral field, you're not allowed to add a massive term. But once we have written our chiral Lagrangian like this, with a right-handed part that doesn't couple to the gauge field and a left-handed part, we may as well add Pauli Villars regulator fields, and that's what we're gonna do. Well, we're gonna do this tomorrow. Okay, so we stop here, and we do this computation tomorrow. Okay. More questions? Yes. Well, the Lagrangian classically is gauge invariant, yes. For the same reason as always, this thing here. So I mean, I can, well, psi L goes to e to the I epsilon alpha T alpha psi L. These are my gauge generators, and they commute with a gamma 5. So T alpha and PL commute, right? So if this was for my psi, for my Dirac fermion, I may just project it, this moves through. So they transform in the usual way, and the derivative on the e to the I epsilon will give a d mu epsilon term, but the a mu transforms into a mu plus d mu epsilon, which cancels the additional term. Yes, that's gauge invariant. Classically, there's no problem, of course. Okay, it's once we quantize that things get more complicated. Okay.